Okay, let me know if you hear too much background noise from the street because the window's open and I can close it. So, and sometimes it's gets to be too much for the audience. So just let me know. So we're going to have a standard type of allocation problem. There's going to be one unit to allocate. The simplest version to think of is an organization like a university that has something to give to one unit within the enterprise. So in this case, it's going to be a dean who has a job slot to give to one department, and there are n departments out there. And the value to giving the slot to department I depends on I's candidates, and that's going to be denoted VI. Sorry, got muted somehow. The problem is that no one knows the VIs, including the agents themselves. The department, the agent, can learn the value at a cost. And learning in this model is evidence. So if you learn something, you can prove it to the mechanism designer, to the dean in this case. By the way, as was said, please feel free to ask questions. Okay, there's one simple solution. Just ask the departments to give the evidence and give it to the best. For now, we're going to assume that the departments are symmetric. And in the talk, I'll have two parts, a symmetric part and an asymmetric. The symmetric is easier, so that's what we're going to start with. So assuming the symmetric situation, if the cost they face is bigger than 1 over n, then we can't get them to respond. I should say here the value to the department of getting the slot is being normalized to 1. Okay, so for the department, if they get the slot, it's worth 1 to them. For the dean, it's worth VI if it's department I. So if the cost is greater than 1 over n, the chance of getting the slot is, since everything's symmetric, 1 over n. They're not going to invest in getting the information. So the focus of this talk is going to be what is the optimal mechanism in such a situation. Namely, there's one good, there's a bunch of agents. The principal wants to give it to the agent with the highest VI. The agents have a cost to getting the information that tells them what their VI is and also enables proving it to the designer. Note that the VI, the value to the designer, to the principal, to the dean, is not necessarily the same as to the department. We're normalizing the department's value of a slot at 1, and the dean's value is that unknown value VI. Oops. Oops. Okay. What would a standard approach be? A standard approach be, we have a mechanism as an auction. Okay. From our purposes, there are two main drawbacks to this. First, we're considering exchanges or decisions within an organization, and transferring money within an organization has other efficiency costs. You may want to give money to a department for doing its teaching activities, doing its research activities, doing all sorts of other activities. Telling it that it has to use the money in order to bid for a slot in order to get a candidate could be distortionary. The second reason, and I think even the much more important one, is that the department and the dean may not agree on the value. Standard auction theory has that the auctioneer wants the money and the department wants the slot, and there's no, the auctioneer doesn't care who gets it. In our case, the auctioneer, the dean, cares a lot about who gets the slot. Okay, and his value, as I said, is VI, which is not necessarily the same. We view this as a general problem in organizational economics. Units in the organization have different goals in the overall organization. Monetary transfers have limited role within organizations, but allocations do need to take place within organizations. Okay. What's another thing that you might do? Well, a very simple solution would be to exclude some departments from consideration. If we restrict attention to approximately 1 over C departments so that the expectation of getting of the expected cost is the same as the expected gain, then all those departments will be willing to respond. Okay, so it's very easy, just tell the 1 over C, this is the largest integer just below 1 over C to be precise. You get information, tell the rest go away, they present their evidence, you give it to the highest one. But clearly there's a potential loss there because there's lots of other departments which may have higher values and we're just excluding them randomly because we don't know which ones to include. We'll see that it's not optimal, in fact, to do this. What is optimal? The dean's going to pick a department. In the symmetric case, the dean's going to be picking a department at random and asking it to learn and provide evidence of its VI. There's going to be a threshold V star, which is constant. If VI is greater than that threshold, the department gets the slot and we're done. If it's less, we consider a second department at random and do exactly the same thing with the same exact threshold. If all values of after we've checked everyone end up being below that threshold, then we give it to the highest person of all the people whose we've checked, which is of the whole group. Okay. Are there any questions about what I'm describing as the problem and what I'm claiming is the optimal solution in the symmetric case? Great.
You use the definite article. So does that mean this is supposed to be uniquely optimal?
Did I?
You said it verbally.
Okay, yeah. No, an optimal mechanism. This is the symmetric optimal mechanism. There may be asymmetric mechanisms that yield exactly the same in some cases. Okay, so it's possible that there are other ones. So yes, I should have been a little more as cautious as this. My verbal version should be as cautious as the slides. Thanks for catching that. Just to give an intuition for the randomization part, not for the fact of why it's sequential in this way, certainly not for the fact why the threshold is constant, which is a little tricky, but just for an intuition for why we have, why we want to randomize. Imagine that we didn't randomize and we went in sequence across individuals, okay? Then the last person to go knows that everybody before them was below the threshold. So they know they have a better than even chance of winning, better than 1 over n. So even if their costs were higher, they would be willing. But since the cost is not higher, that means that there's a slack there and we're not taking advantage of it. If we randomize without telling anybody where their place is in the randomization, everybody gets a certain chance, thinks that with some probability they're last, and therefore they get some of that benefit. And they think they're second to last, which has not as big a benefit, but some benefit as well. Okay, so we symmetrize that gain of being last among everyone, and that way we use that slack and distribute it among all the players. Okay, so that's why randomization can be useful. Okay, so I'm going to go through the model very quickly through related literature, mentioning only 2 papers really with any significance. Because there are only 2 that are somewhat close. And then I'm going to divide the substance of the talk of the results into 4 parts. First, there's going to be a characterization of the set of feasible outcomes. This is not obvious. We have to say, what is the set of things that we can attain using some mechanisms? I'll make clear why it's not obvious when we get there. Then once we know what the feasible set is, we're going to describe what the optimal mechanism is in the symmetric case and what the optimal mechanism is in the asymmetric case. Okay, we're going to give some comparative statics, quite a few for the symmetric because that one we've solved completely, and a few for the asymmetric because that one is still a bit up in the air. There'll be some conjectures, some answers, and some things we're not sure about yet. And then I'll conclude. So as I said, the model is very simple and very standard. There are n agents and 1 principal. The principal has 1 unit to give to an agent. The value to the principal of giving the good is VI. The value to the agent of getting it is normalized to 1. Up till now, very standard auction environment. We add to that the agents don't know their VIs. That's also not standard, but there's other work that has looked at that in the auction environment. And there's going to be a cost for learning that. And in addition, which is a somewhat less standard, is the learning gives evidence so that the agent can prove what he's learned to the principal. One way to interpret learning is that you get information, a signal, which determines what your belief is about the value to you. And you can present that signal to the principal. In the case of a department, that's very simple. You collect letters, you collect information, and you have a committee that writes a report, and you can present all of that information just the way you present it to your colleagues in the department. You can present that to the dean as evidence. Okay. Related literature, there's a bunch of papers that are peripherally or in some way related. First of all, there's a lot of literature on just the principles or properties of mechanism design with evidence. Starting from Green-Lafont in 1986, there's a whole bunch of papers. This isn't all of them. These are mostly about the ideas of the revelation principle and the structure of the theoretical structure of mechanism design with evidence. Then there are more specific models about specific cases of studying evidence acquisition, or you could think of it as testing. These are usually games, specific games. They're not mechanism design. They're not someone trying to find an optimal mechanism, but rather saying if agents are playing a game that has evidence acquisition or testing in it, then this is how it will look. Then we get to things which are closer. There's mechanism design with information acquisition. Of course, there's a lot of stuff on auctions, as I just mentioned, which would be the more standard type, and that's within, that can be seen in a survey by Bergman Velomaki. The two closest papers are one by Gershkov and Sentes and another by Kremer, Spiegel, and Zhang. Okay, so in the this paper is about voting, but it has one thing very much in common with us. It has a random order that's hidden from the agents in order to help with incentives. So that is a feature that already exists in the literature and in particular in that paper. It's, however, a very different environment. In particular, they study a public good. There's no evidence. And in addition, they assume ex post efficiency. So the mechanism they find is not an overall optimal mechanism. Okay. So that for all three of these reasons, the answers that they get are very distinct from ours, although they do have in common this feature. Kremer, Spiegel, and Zhang do study a private good like we do. They do have an optimal mechanism, and in their optimal mechanism, the agents are approached sequentially using a threshold. So that's similar in structure. But the model is extremely different. And the main reason it's different is because they allow transfers. And on top of allowing transfers, it's not just the allowing of transfers, they allow transfers before there's any asymmetric information. So the principal can extract the full surplus because there's no asymmetric information. Once the principal can extract the full surplus, that means he's facing a problem of designing after the surplus extraction the most efficient thing without any distortions because he internalizes all of the costs. Okay. Since he's internalizing all of the costs, and this becomes a search problem, and what he does is you solve the Weitzman search problem, and you solve it. It's not trivial to solve, but they solve it for that environment, and then they say that's what we're going to do after we get the money from you. So we're going to allocate efficiently using the Weitzman solution to the search problem, and now bid to us your expected gain from that efficient allocation. Okay, so that's very different from what we're doing. But as I said, we do have the private good and problem in common. We do approach sequentially. We do use a threshold. Okay. The first thing we're going to do is characterize the feasible outcomes. We're going to do that with keeping in mind that this is a complicated problem. Okay, so this is in our, to be honest, at first we started with a much more complicated problem, thinking this one would be too simple. Having not been able to solve the complicated one, we turned to this one and discovered that this one is pretty complicated in itself, because there's both a sequential search problem and an incentive problem combined. Because you want to incentivize the agents to get the information, and you're searching among them. Okay, so in the symmetric case, which is the one I'm going to start with, we don't have the difficult question of how do we do that? How do we do the search really? Okay, we're just providing the incentives and a stopping rule. Okay, in the more complicated case, there's a question of whom do you start with and how do you decide upon that? In particular, even in the symmetric case, the threshold, which I said is constant, could depend on history. We'll see that it doesn't, but you could. So we're going to do, as is usual in mechanism design, a two-stage process. First, we're going to look at the structure of the game. What can we say about the optimal structure of the game? And then we're going to look at the actual allocation, optimal allocation that arises. And it turns out, like in much other mechanism design problems, it's useful to look at interim allocations. You'll see why in a bit, but we're going to get there. It turns out that that helps us a lot, and that's going to be what we're going to be used to characterize the feasible outcomes. So what is the game form that we're going to study? We're not going to define it in great detail because we don't need the notation. Well, but we can say very simply in words the essential pieces. First, we're going to apply the revelation principle. We're going to focus on direct mechanisms where the agents recruit truthfully and obey the principle's instructions. What does obey mean? The principle is going to say, you get evidence now and present it to me. The agent's going to get evidence and present it. Okay. There isn't cheap talk at the beginning because the agent doesn't know anything until they get the evidence. So there's no issue of truthful reporting ex ante. The only time that there's any truthfulness involved is I tell you to get the evidence and you get the evidence and show it to me. Okay, since there's no, in this model, there's only there's no way of manipulating the evidence. That would be an extension. That's going to be when I talk about conclusions, things that we could think about for the future. So the agent gets a piece of evidence, and that is the evidence that he presents. There's no choice of which evidence to present. Okay. What we want to do, of course, is provide the maximal punishment in case the agent doesn't do what we ask him to. And what's the maximal punishment here? There's no transfer. So the maximal punishment is just not giving the good. So if we ask for evidence and it's not given, the agent doesn't get the good. Okay. So that's the first part of our conclusions about what the mechanism looks like. Second, sequential is without loss of generality. There's no discounting. And there's no reason to ask more than one agent at a time. So without loss of generality, we're going to approach them sequentially. Not deterministically, that is with loss of generality, but sequentially. It's also without loss of generality to give one information set per agent, okay? Meaning that if we tell them to get evidence at one point and show it to us after, say, let's say there's 3 people, and we start with 50% with agent A, 30% with B, and then we go to C. If we tell C to get evidence after agent A sometimes, and sometimes after agent B, then standard arguments that you want to pool tell you that you want to tell the agent, you don't want to tell the agent which environment it is that you're asking in, just you're saying, give me evidence. Okay, so I hope that was clear. Let me just describe it. Okay, let's say we start with A or B with 50% probability, and then depending on A's values, we sometimes stop and sometimes go to C. And here we sometimes stop and sometimes go to C. What I'm saying is this is going to be one common information set. Okay. There's another aspect of pooling, which is we could imagine the agent having a degenerate information set where we don't ask for evidence and just give them the good. That's also silly because we might as well pool that case where we're sometimes giving them the good with whatever occasions we're asking them for evidence. So if we ask for evidence sometimes, then we're never going to give them the good without asking for evidence. Okay? So these are 4 properties, which I'll summarize in this slightly long paragraph. We're going to use a direct sequential mechanism in which each agent has at most one information set at which she alone is asked to get evidence. And if asked, she never gets the good without being asked. When asked, she does what's been asked of her and reports truthfully. If they don't provide the evidence, then they don't get the good. That's a summary of the structure that we're going to use. So now I can talk about allocations. Isn't that working? Okay. We're going to start with an ex post allocation. There's an asterisk here because this is, and it's in parentheses to avoid confusion and to remind me to highlight the fact that this is ex post in the sense that it is after all the agents know their values or all the values are known, but it's not ex post after all uncertainty has been realized. Okay, so I'm describing an allocation here has 2 features, the allocation of the good and the evidence probabilities. The allocation of the good is going to be a function from the vector of values into a probability, which says the probability that I gets the good, given that that's the vector of values. Okay, and the sum of those probabilities obviously has to be less than or equal to 1, since we only have one good to allocate. Okay, so this is what I mean by the ex post allocation of the good. Any question about this? We're now getting a little more into nitty gritty. So once this is getting to be points where if something's unclear, it's best to ask. The other feature, so the star is because there is uncertainty. I'm allowing for, it's not ex post in the sense of after everything, it's after values. Okay. The second feature of the ex post allocation is the evidence probabilities. And the evidence probability is the probability with which I ask person I for evidence. And this can depend at most on everybody else's values. Okay. Obviously, it can't depend on I's own value, because if we're asking I for evidence, it's before I knows his or her value. But in addition, it can't depend, it's not true that it can always depend on everybody's values. I think I have an example. In particular, it's not true that every possible p hat and e hat, which are functions of these forms, can be generated by some game. For example, I can't ask person I, if let's imagine there's only two people, I can't ask each of the I's, 1 and 2, for evidence if and only if the other person's value is less than a half. That is a function of this form, but it's not feasible. There is no game form which would enable that. Because if I want to ask person 1 only when 2's value is less than a half, then I have to ask 2 first. If I want to ask 2 only when 1's values are less than a half, I have to ask 1 first. I can't ask both 1 and 2 first. So there's no game form which would generate that ex post function. So note that in contrast to the standard model of auctions without evidence, where we just have this, in which there's no question what functions can be realized. Because if you know the values, you can realize any function of this form. In our environment, even the ex post functions, what the class of ex post functions of evidence collection, which class is feasible using some game form, is not at all obvious. Okay? So normally we turn then to interim values in the ex post and say, okay, we know that we can get any ex post, which interim can we get? That's something that's often done in the mechanism design literature. We're going to do now the exact same thing, but I just want to highlight, even in the ex post environment, there isn't a simple statement of what is the set of feasible functions of allocation of the good and collecting evidence. Okay. Given the lack of questions and the fact that there's a little number 7 in the corner in my screen, I'm assuming that people are chatting with Bart and asking him questions or somebody else. Okay.
Correct.
So as I said, we're going to turn to interim allocations. So thanks, Bart, for fielding all of those. We're going to define interim allocations in the usual way. PI of VI is the expected probability that type VI of player I gets of the good. In other words, we have an ex post probability P hat, which depends on I's value and everyone else's. We take the expectation over everybody else, and we get I's interim expected probability of getting the good. Okay, this is a standard definition. Is there any question about that definition? Good point to stop. Okay, same thing about evidence. Evidence, and remember that evidence is not a function of your own value, because it can't be, because you don't know it yet when you're getting the evidence. So we just take the expectation over everybody else using our ex post evidence and call that the interim evidence probability. This is what I'm going to call an interim allocation. A pair PE, which is a vector for each player. It's the P's are going to be a function of their values, the expected probability of getting the good. The E's are the expected probability of being asked for evidence. Again, we don't know yet what's the set of E's that we can obtain, because we don't even know yet what's the set of E hats that we can obtain. That's going to be what this section of the talk is about, namely, what's the feasible set. I want to point out that once we've translated everything to the interim, we can translate all the constraints and the objectives to the interim as well. So if we knew what the set of interim allocations, are, what the feasible set is, we could solve try to solve the problem from the interim perspective. So what's the principal's payoff? It's the expectation over all values of what he gets. What is he going to get? Well, if person I gets it and person I's value is VI, and they get the good with probability ex post probability P hat I of VI. There's a VI. Oh no, there's a V there. Pi hat of V, which is the vector of everybody's values. And we average that across, we add that up over all I's, and we take the expectation over all possible value vectors. Okay, so this is written in terms of the ex post. Obviously, we can rewrite it in terms of the interim, just as the expected interim payoffs to the players. The expected interim probabilities of the players times their values. Sorry, not their payoffs. Their payoffs would be without the VIs. So this is the principal payoff. This is what's going to be in our objective function. The expected value that the principal gets from the allocations. Okay. By the way, Bart, one thing, you should interrupt me if you're getting the same question a dozen times, then tell me to repeat something so that everybody hears it. Okay. How about incentive compatibility? Incentive compatibility is very simple. It just says that I's expected probability of getting the good. In other words, this is his interim probability of getting the good if he has value VI. This is the expectation over all his values. So this is the expected probability of getting the good. This is the expected probability of being asked for evidence. This is the cost of evidence. So this in total, this in total has to be non-negative. As long as this is non-negative, then the agent will be willing to engage in the mechanism. When asked for evidence, will be providing it because his expected return from providing the evidence is bigger than the expected cost of getting the evidence. Okay? So we want to maximize this. Sorry, we want to maximize this subject to this and feasibility. Okay, but what is feasible? So that's what we're turning to now. Okay. So the first part that's obviously necessary has nothing to do with us in the sense that this has been done decades ago by Kim Border, and he showed that the P, forgetting about evidence completely for now, what is the set of interim P's that you can get? Okay, so he showed that there is a function that given a collection of functions P, there is an allocation, meaning there is a way to allocate the good, which will give those P's if and only if they satisfy what are called the border conditions. I am not going to write down the border conditions because this is not a seminar in Kim's paper, okay? Most of you are too young to have heard the seminar from Kim, but that's and they didn't record it then, but that's your tough luck. Now you get stuck with reading the paper. There's dozens of papers on the topic with all sorts of simplifications and complications, two of which we needed to take advantage of. Okay, I'll get to that later. Okay, this is clearly a necessary condition. If given a P, there's no ex post way to generate that P, obviously we can't get it. Okay, so clearly this is going to be a necessary condition. Now there's going to be another necessary condition. The other necessary condition is on the evidence. This is new to this segment, to this type of talk. What's the condition on evidence? Either we don't ask for it, in which case the P is a constant function, or we ask for it, in which case the probability with we ask for it has to be the probability that we give it, because we can't know the evidence unless we ask for it. So we have to ask for it with at least the probability with which we are giving the good. Okay. This is the important condition. This one we're going to be basically ignoring because it's not the interesting case. So this is the condition that I want you to understand. So if P is not constant, the principal has to be asking evidence. Okay. So I never gets the good without, why did that disappear? I never gets the good without asking for evidence. without being asked for evidence, sorry, I never gets the good without being asked for evidence. So the probability of getting the good for every possible value that might realize has to be less than the probability with which you ask for evidence. Or in other words, the max among these has to be less than that. Okay. Intuitively, you're going to want to set it to be equal. Why? Because you don't want to ask for evidence more than is necessary. So if you're asking for it, you ought to be giving it. Okay, that's within the, that rough intuition was there when I talked about the general game form structure, but I didn't specify it. But in terms of what the constraint is, this is the constraint. Okay. It's far less obvious, in fact, was far less obvious to us for a very long time, that these are the sufficient conditions. Any PE satisfying these two conditions can be generated by some game form. Okay. Now, remind me how long the seminar is?
Oh, we started 15 minutes late, so you have 1 hour. So
I have an hour.
approximately halfway through, yes.
Yeah, but I'm leaving questions at the, if you wanted also some time for questions at the end, and some people might, I'm trying to decide whether to click on this link or not.
Do it.
Don't, no.
Who said do it?
I did, yeah.
Francisco?
Yeah. Just do whatever
Yeah,
you
go,
think is
go,
right.
go.
You have a half an hour.
It's the last seminar of the series, so we can be a bit more relaxed with the rules.
Also, questions are in additional to this 1 hour.
Okay. Yeah, so I'll figure it out. We'll find a way to get, I'm not going to spend a lot of time on this, but I'll give the gist of it. I'm not giving Border's definition, so this is not a way to learn about Border. This is a way to learn why that extra condition that we impose doesn't cause problems with his theorem. So what he showed is that every interim allocation is a convex combination of hierarchical allocations. And he showed that hierarchical allocations are very easy to get. Okay, what is a hierarchical allocation? It's one which, given any profile V, we rank the individuals and give the good to the I with the highest type. It's not according to the V. There's a ranking. That's the idea of a hierarchy. We just choose the person with the highest type if that is the profile. Okay. And he showed that every interim allocation that's feasible, to be precise, every feasible interim allocation is a convex combination of hierarchical ones. Okay. Now it's very easy to generate. So what's a hierarchical allocation? Hierarchical allocation is one in which for every profile, there's a ranking who gets the good. It's very easy to see that a hierarchical allocation that satisfies our evidence constraint can be feasible. Okay, so let's go through the idea of that. The highest ranked type must be getting the good with probability 1. So that means that that agent must be looked at with probability 1. So we're going to ask that agent first, and we'll give the good if she has that type, which is supposed to give it to her with probability 1. Okay. Then we'll look who's the second highest type. That type must get the good with the probability that she doesn't face the highest type, right? That we didn't already give it. So all the remaining probability that we have must be going to the next ranked person. So ask them next. Okay. That means that the probability that they're being asked is the probability that we didn't already give it. And that's the probability with which we're giving it to them. So their P is going, their E is going to be, EI is going to be greater than that PI of VI, which is their maximal VI, PI of VI, because we're going in sequence. Okay. And we continue in that order. So what I'm saying here is any hierarchical allocation that satisfies the constraint that we imposed, namely EI has to be greater than or equal to PI of VI for all VI, and in particular for the VI that maximizes that, any hierarchical allocation, any P that's hierarchical and any E that satisfies what I just said is the evidence constraint, can be implemented by hierarchical game form. Okay. And that seems like it gives us the answer, because Border showed, where'd that go? Border showed that every feasible interim allocation is a convex combination of hierarchical allocations. Every hierarchical allocation that satisfies the evidence constraints can be gotten. So just take convex combinations and we're done. Okay, not quite. Okay, it looks like that would be enough, but there's a complication. When we take convex combinations of hierarchical mechanisms, each of which satisfy the evidence constraint, the convex combination may not. Okay, so to make that precise, let's consider two hierarchies. The hierarchy H, in which we get, there's only one player really, player I, and there's only two types, VI and VI prime. And in H, we give it to VI with probability 1, and in H prime, we give it to VI prime with probability 1. Okay. So in H, we need EI to be 1, and the evidence constraint EI greater than PI of VI gives us that, because PI of VI is 1 and EI is 1, and that's so we're on solid ground. So we have this hierarchy, this hierarchical mechanism, and yes, if the evidence constraint is satisfied, in other words, if EI is greater than PI of VI, since PI of VI is 1, EI has to be 1, and we're asking person I first, and we need to because we want to give him the good sometimes with probability 1. Okay? Now let's look at H prime. H prime is exactly the same, except I switched VI and VI prime, so exactly the same is true. We need to ask I with probability 1, and the constraint PI of VI, EI greater than PI of VI, in that case will be EI, the binding one will be EI greater than or equal to PI of VI prime, which is equal to 1. So that'll give us EI at least 1, and that'll give us that we start with player I with probability 1, and all is fine. But now imagine that you take a 50-50 mix of those two hierarchies. That 50-50 mix has each PI getting the good with probability 1/2. Each VI getting. So PI of VI is equal to PI of VI prime is equal to 1/2. But we still need to start with player I, because either we're going to H, in which case we're giving it to I, or we're going to H prime, in which case we're giving it to I. So either mechanism that we choose, player I has to be started with probability 1. Okay? But the evidence constraint only tells us now EI greater than or equal to 1/2. It is not sufficient. So we have a problem. Border's result doesn't give us what we need. Okay? So it turns out that this works, and it works because of what's written here. Okay? It turns out we can restrict to hierarchical mechanisms that have the same hierarchy of I's types in each mechanism. So when we're looking at a feasible mechanism, every feasible mechanism can be generated, like Border said, by a convex combination of hierarchical allocations, in which in every hierarchical allocations, we order I's types the same way. And then that problem doesn't come up. Okay, so this was the T-tour that Bart didn't want me to do, so I will now go back. Come on, go back. Okay, and this tells us why any PE satisfying Border and what I'll call the evidence condition, PI of, VI less than or equal to EI for all VI, these conditions are the sufficient conditions. Okay, I'm being a tiny bit sloppy because it wasn't exactly this condition. It was either it's constant or this condition. Okay, in a minute, I'm going to make an assumption to get rid of that either so that I can just work with this condition. It's just going to avoid a class of what we expect, haven't solved for it, so we can't be sure, but we expect are not going to be very interesting, a very interesting case. So what we're going to do is we're going to assume that CI is less than 1. Okay. In that case, we don't need to worry about PI being a positive constant. In that case, we're going to, in that case, we can take the constraint to be what I said before. So whenever I say the evidence constraint, this is what I mean. Okay. And this is the constraint. So now I think now I'm going to say one more thing. So now we're going to use the evidence constraint to simplify the problem. And how? Remember that this was what incentive compatibility said. And if we look here, we have another inequality. We're going to just chain these two together. We know that for every VI prime, PI of VI prime has to be less than or equal to EI. So if we divide through by CI, we get that PI VI prime has to be less than or equal to this. Okay, this is the IC constraint. This is the evidence constraint. Jointly, they give us this constraint. And now we can rewrite our problem in a much easier to solve way. Okay. The principal's problem is what we wrote before, namely maximizes expected payoff. He gets VI if type VI of I gets the good. That happens with probability PI of VI. That's the interim probability for player I. We're looking for the P's that are feasible, satisfy the border condition, and satisfy this combined evidence constraint and incentive compatibility condition. Okay, so if we have this, we know that we can squeeze the EI in between, and therefore we can satisfy both the IC and the feasibility conditions. So now this is our problem. Okay, so all of that was just to rewrite the problem in the interim form. Now we can talk about the solution. Okay. So first off, we're going to talk about the symmetric case. So the distributions of values are the same for everybody, and the costs are going to be the same for everybody. And as I said, we're going to be assuming the cost is less than 1, so that we can restrict attention to the simplified evidence condition, not talk about the case where we might want to give it to somebody with positive probability without checking them. And we're going to have it be strictly positive, so that it's an interesting case, because if the cost is 0, obviously you're going to get that person's evidence first and then move on to the rest of the problem. Okay. In this subsection, V and P are not profiles. They're not vectors for each individual. They're just for a representative agent. Okay. It's kind of obvious that the principal is not going to keep the good because everybody has value. Okay, I should have said F has support on the positives. So there's no probability of having a negative outcome. So the principal never wants to withhold the good. Since we're looking at the symmetric problem, the expectation of a random individual of getting the good is just 1 over n. Okay, we're looking at the optimal symmetric mechanism. Okay. So what's the principal's problem in this symmetric case? We want to maximize the expected return to the principal. This is the value that might occur. This is the probability of giving to that value. We're looking for the P's that maximize this expression, subject to the border conditions and subject to the evidence constraint. It's really the combined evidence feasibility constraint. P of V less than or equal to 1 over n times C, okay, for all V. So this is the new constraint. This is the novel feature of our problem. And we're going to see in a minute what it tells us. Imagine that there was no evidence issue. You knew the agent's values. Then what would you do? You'd give it to the agent that has the highest value. That's very simple. So what's the probability? What's the interim probability on the vertical axis here? I have interim probabilities. So what's the probability of a random particular agent? Let's look at agent number 1 of getting the good when in the best possible scenario, when this value is the highest possible value. Okay. Then it's going to be 1 because everybody's going to be below him. Okay. Now, this is a continuous problem, but you can think of it discretely. If there was if we do this discretely, then there's a problem of ties, which this gets rid of by looking at the continuum. If there were possibly ties, then they would get it with 1 over n times the probability that everybody that others at this have the highest value as well. Okay, so it wouldn't quite be probability 1. It would be something below, and it would be a step. What would the next step be? The next step is the probability that with the second highest value. So this is the highest value. Here we have imagine discretizing it. We have the second highest value. What's the probability of the second highest value person of a person getting the good when he's the second highest value? It's the probability that everybody is below him. So that's why we have here FV to the n minus 1. That's the interim probabilities of agent 1, say, getting the good in the first best, namely when there's no evidence issue, when I know the values of everybody. Okay. Now we can ask how that's going to change in our environment. Okay. I want to just make a remark. These are interim probabilities, right? So Border's condition would tell us that this is feasible. Okay. And I told you that it's feasible because I told you how we're going to do it. If we know the values, we give it to the highest and the next highest and the next highest and so on. Border's conditions are exactly how to do this, are exactly what functions are feasible. Okay. I didn't have to use it in describing this because I told you exactly how to do it. But in the abstract, what is the set of feasible things? That's going to be told to us by Border. But we have an additional constraint. And the additional constraint is we can't go above 1 over NC. So let's change colors. We can't go up here because the evidence probability has to be greater than the probability of giving the good to agent I when his value is VI has to be greater than, less than or equal to 1 over NC. Just to remind you, that was this condition over here. And that came from the combined feasibility and evidence constraint. So even though I expect that by now you've forgotten exactly the argument for why that's the condition, just remember that that's the condition. We can't go above this. Okay, so clearly we have to chop this off and move it down to here. And clearly it would be feasible at that point to continue with these probabilities if we wanted to. But we can do better because we have leftover probability. Remember what Border's conditions tell us is what is the function that we can get. This is the function we can get because we're allocating it to the highest. And if the highest isn't there, to the next highest. And if the next highest isn't there, to the third highest, and so on. Okay. If we take away those probabilities of giving it to the highest types, we can use some of that in giving it to more of the lower types. So we want to continue at our constraint as much as possible. What does as much as possible means? It means that the expected probability of giving it here has to equal the expected probability, of giving it here. Okay, so our solution is going to be give it as to the highest type, the interim allocation. This doesn't tell us anything yet about what the allocation, how we achieve this, what the mechanism is. I'm going to get to that. But what it's telling us is the interim allocation has been constrained in this way. We're going to continue at this height as long as we can. And then we'll jump down to if nobody is above this threshold, and above this threshold, everybody gets it with this common probability. If nobody's above that threshold, then we go back to looking at everybody and giving it to the person who has the highest among those who are below that threshold. Okay, and that threshold, as I said, comes from calculating that the probability of allocating it to this group of types in this way is the same as the probability of allocating to this group of types. Sorry, to this group of the same group of types in this way. Okay, so that is exactly the solution to our problem in terms of interim probabilities. Of course, that doesn't tell us what the solution looks like. So if we want to do comparative statics or have a sense of the mechanism, we still have some work to do. But at least we found the interim probabilities, and this shows you the benefit of using that result of border and the modification that comes out of adding evidence issues to the border environment. Okay, I'm also going to draw here another function. And what's this? This is the function of what would happen if we excluded it and asked everybody as many as we can, and stop there. The cost is 1/2, so we could ask 2 people with probability 1. If we ask 2 people with probability 1, then the interim probabilities look exactly as they do in this picture. Okay. Notice that they are lower than the upper ones and higher than the lower ones. So this exclusion method does better here and worse here. Okay. But since this exclusion method has the same overall probabilities of allocating, this is a mean preserving spread of this, which is a good thing. I'm going to say that in a different terminology later, but this is the picture which captures that idea. We gain at the upper end, we lose at the lower end. This is good for us on average.
Eddie, you have about 7 minutes more.
Then I definitely messed up my calculations. Okay. So Bart was right. Shouldn't have gone to the border. He's always right. What can I say?
Exactly, exactly. I was waiting for that.
So we have a threshold which satisfies an equation which equates those probabilities. Don't stare at it too long. Just trust me, it does that. And what we're going to do is the interim probability is going to allocate at that bound above the threshold and to the highest person possible below the threshold. Okay? So now we're going to point out that what I call the optimal mechanism does generate this. Remember what I said is the optimal mechanism. We're going to choose an agent at random to go first. They get the good if they're above a threshold. Obviously, the threshold I'm going to use is the V star in this picture. Okay? So I'm going to choose an agent at random. If they're above the threshold, I'm going to give them the good. If they're below the threshold, I'll go on. If everybody's below the threshold, I'll give it to the highest one. So overall, what am I doing? I'm giving it with some constant probability. I haven't yet shown it's this. That's why I'm crossing it out. If I had shown that it's this, it would show you that this mechanism that I describe achieves exactly the optimal interim probabilities and hence is the optimal mechanism. All I've said is it's constant, the mechanism that I've described. Below, I have shown that it does this. Okay. How do we know that it matches? Okay. What is V star doing? It's making those probabilities equal. It turns out that that's exactly giving us the condition. I won't explain the algebra behind why that constant that this gives us is exactly 1 over NC. Okay, but that's explained briefly in the slides if you want to look at it. I'll now say a few things about comparative statics. The first is, if this cost goes up, then the threshold has to fall. If the values go up, then the threshold will go up. If the number of agent goes up, the threshold will fall. Okay. Let's focus on this one. For the intuition for these are clear. If the cost goes up, I have to give the agent the good with a higher probability when I approach him. Okay, so I have to lower the threshold so that they know that when I've approached them, the chance of them getting the good has gone up. Okay, the lower the threshold, the more likely it is. If the threshold is 0, then that means the first person I approach gets the good for sure. So that all follows from this equation very directly. If the number of agent goes up, then if we were to keep the threshold the same, then everything's fine up until we get to the point where we've asked everybody. But when we've asked everybody, then this agent is worse off because there's more agents, so he's less likely to be in good shape. He's less likely to be at the top. Therefore, we have to make things better for him at the first stage, namely at the threshold stage. So we're going to have to lower the threshold just like when the cost went up. This seems a little counterintuitive. If there's more players, then I'm lowering the threshold. Lowering the threshold is a bad thing for the principal. He doesn't like this because the lower the threshold, the more often he's giving the good to the agents before checking other agents. So maybe we do want to exclude. Okay. Well, what's the expected probability of what's the probability you ask an agent for evidence? 1 over NC. So what's the expected number of people you ask for evidence? It doesn't depend on the number of agents. This is constant, okay, in our class of optimal mechanisms. What we're doing by enlarging n, it's true we're lowering the threshold, but we're getting that mean preserving spread. We're conditioning our ask by lowering the threshold. What we're achieving and having more agents is we're asking more agents when it's worthwhile to do so. We're asking fewer agents when we don't want to do so. Okay, that was a big fast. I've got about 3 minutes left.
Yes.
Okay. So, let's draw this picture first. So what happens in the asymmetric case? Let's talk about 2 agents and let's draw a picture. I'm drawing a picture here of 1's costs on the horizontal axis. 2's costs are constant at 0.7. So at this point, the agents are symmetric. I'm also using the same distribution for the agents. So at this point, the agents' costs are equal. And we're at the optimal allocation of the 4, meaning we're going to randomize 50-50. And on this axis, I have the probability of going to an agent. We're going to randomize 50-50 and do what we said before. What's going to happen in the more general mechanism? First of all, we won't be randomizing necessarily 50-50. We might start with 1 if his costs are low enough. We might start with 2 if his costs are high enough. And we might randomize somewhere in between if the costs are in the middle. But there's another aspect to the problem that changes. In addition to having a threshold, each agent is now going to have so this is the threshold that I've drawn here. Each agent is now going to have a virtual value. Okay, and that's virtual value is what we're going to compare to the threshold. So each agent is going to have a virtual value VI star, which we're going to compare and we're going to compare that to the actual V. The virtual value will be their true value plus some difference. They're going to get a bonus or a penalty depending on the problem. Okay, that penalty is constant for all of their values. So each agent is going to have, we're going to look at their value plus a constant, which can be found given the parameters of the problem. That constant plus the value, I should just be writing it, is their virtual value. We do 2 things with that virtual value. We use it to compare to the threshold. And if no one is above the threshold and we get to the end, then we allocate it according to the virtual values, not the actual values. I'm using Meyerson's terminology of virtual values because it has that idea of not using the actual value. It's not the virtual value in Meyerson's calculation at all. There's no connection between his calculation and what we're doing. But the idea that you give a person a bonus due to the incentive problem is the same, a bonus or penalty. So every agent will be allocated a bonus or penalty. We're going to compare that to the threshold, and we're going to use that to compare among them if we get to the end. Okay. And at this point, we have a bunch of cute, I think, very cute and interesting comparative statics about how the solution looks. Namely, it looks, where'd the picture go? Something like this in general, okay? Where something like this in general means this part and this part and this part and this part are completely general. Sorry, all the black. The reds, we think this is general, but haven't been able to prove that. And I think I should stop here since I'm really running out of time and just rushing through. But the interesting questions here are things like, when one's costs go down, do we approach one more often? If we're approaching one more often, how do we do so? Because there are two ways that one gets approached. One is the probability that we start with one. The other is if we start with two and two is below two's threshold, then we go to one. So we could go to one more often either by changing two's threshold or by changing the initial probability. Which one and how and so on. So that's what we're exploring now. We've got a couple of results. Since this was recorded in the end, you can, oh no, the screen, I didn't get to them, so that doesn't help much. I can post the slides so you can look at the slides for seeing what results we have and where we're headed. Okay, and I'll leave it at that.
Okay, well, thank you very much. Again, apologies to everyone, including especially you, Eddie, and Bart. Elchanan tried to log in, but couldn't. So we had a long exchange of emails, but we couldn't make it work. So does anybody have any questions? I'm happy to keep the recording going on for a few more minutes to allow for some questions. Just unmute yourselves.
In the sequential mechanism, do you hear me? Yeah.
Yes.
In the sequential mechanism, does it matter that you don't tell the agent the order? I mean, if I knew I was the...
Yes, and I'll explain why. Yes, it matters a lot. This is related to the pooling that I talked about. Namely, imagine there's only two agents, and I'm going to 50-50 start with one or with two. When I start with two, and then one knows that I started with two, one is happy upon being asked for evidence. Not happy overall, I'm not caring about their joy. I'm just saying, assuming I approach them to ask for evidence, they know they're likely to get the good because they know two has a low value. If I start with one, then one doesn't have that extra information. So when I ask one for evidence, if he's first, if I were to tell him, then what I'm doing by we're not telling him is I'm pooling, I'm kind of taking the fact that when he's second, the chances are good that he gets the good conditional on being asked. When he's first, the chances are less good. By pooling the two, I get the average, and that's useful because the constraint is going to be the binding one is whichever's higher. So if I told him that he's first, then I'd be screwed. He wouldn't provide the evidence when he's first. By not telling him, I get the benefit of him being sometimes last. Did that explain it?
Yeah, I have to think about it, but because it looks, at first blush, it would look like, I get it if I'm above V star. And that has nothing to do with whether somebody else was asked before.
So exactly. Yeah, okay, so that helps me explain it better. You don't get it if you're above V star. You get it if you're above V star and you're first. You get it if you're second and above V star and the first was below V star.
Okay, I see. So coming second has this advantage that if I'm below V star, I'm more likely to win because I know that the other guy is below V star. Something like that. Is that?
Yes, exactly. That's exactly it.
Okay, I see. All right. Thank you.
Sure.
Anybody else? While we wait for questions, Eddie, would you be happy to put the slides on our webpage? We can remove them whenever you guys wish to. I don't think there's a paper yet.
Art, you're okay with that?
Sure.
Okay.
Sure.
Okay. So if you could just send them over to us, we'll put them on
Yep,
our.
I'll do so.
And
Yeah, there's no paper yet.
There's no paper yet because
This is the paper by Bart, Elchanan, and me. and we've only been working on it for several years. It's not been a decade yet, so you got to be patient.
Yeah, no. You've got a few papers already. You haven't just been working on this one, have you? So, it's
No, but it takes, it's a good, a decade is a good rough estimate from date of start to date of finish.
It
So
makes me feel very good, very good, very good. It makes mere mortals feel better. Okay, anybody else have questions? Okay, everybody's very shy.
let me just say one thing about this picture that I didn't have time to really talk about. There's a lot of things in it that at first sight look counterintuitive, because there's this kind of non-monotonicity down here, and there's this non-monotonicity over here, and these things look a little odd. We would expect things to be monotonic like this. This is the function which says, what's the probability I'm asking the agent? We haven't yet proven it's monotonic, but we're getting there. We've proven it for some cases, and we're getting there. And this just says that as the player's costs go up, I'll do this instead, imagining someone asked this question. If the costs went up, then the probability you approach that person goes down, because you want to approach the less expensive person first. That's intuitive. And you would think that as this is going down, then so should the threshold, and so should this virtual value feature that you're giving the person as a bonus. But it turns out that that's not true. And there's a switch. And the switch is exactly when this constraint, namely that you can't give it with more probability than 1 or less probability than 0, kicks in. So if this constraint weren't there, so to speak, intuitively, then we'd have this monotonicity here. But what we have is this, it's monotonic in this region, and it's somewhat monotonic is the best I can say in this region. We don't have yet results to say more than that. It's somewhat monotonic, but in the other direction in this intermediate region. And another intuition that I'll give, just to help out, is going to be basic microeconomics. Let's look at the probability with which we're going to player 1, say. As you raise C, you increase the cost of agents 1. Okay, that's the cost for him to get evidence, but that's also the cost you have to pay for approaching him. So you want to approach him less. But you're also poorer, because the total costs in the system have gone up. So there's a substitution effect. You want to approach agent 1 less and go to agent 2, but there's also an income effect. You're more poor. So that's why you're going to get monotonicity on agent 1, because it is not a Giffen good. His price went up, you're going to go to him less. But actually you're going to get a non-monotonicity in general on agent 2, because because there's both an income and a substitution effect, and the income effect can dominate. You might approach agent 2 less overall as well. And so we're hopeful, I'm not sure it'll pan out, but hopefully that micro 101 intuition will turn out to be something we can take advantage of.
Eddie, can I ask another question?
Yes.
Just a second. I'm just going to stop the recording, if that's okay with everybody.
Yeah.
Go ahead.
Okay, go on.
I mean, if it's a silly question, just ignore it. I just was wondering whether